Hi everyone, welcome. We are discussing about the stability of the molecules, stability in the general organic chemistry. We have discussed already about stability of resonating structures. After that, stability of reactive intermediates. Now today's class is stability of heat of hydrogenation. Okay, what is heat of hydrogenation and what is heat of combustion? Stability of alkenes. We don't need to discuss about the stability of alkenes separately. We are going to discuss about the stability of alkenes in this only, in this heat of hydrogenation. Next, if we have still time, stability of conjugated systems. Okay, right. So first of all, what is heat of hydrogenation? What is heat of hydrogenation? That's the point. What is heat of hydrogenation? Okay, so heat of hydrogenation is nothing but conversion of unsaturated systems to saturated systems. What it means? What is unsaturated system? Simple. sp2 system, sp system. When we have double and triple bonds in the molecule, that is unsaturated system. If we do hydrogenation to that particular system, unsaturated system, that unsaturated system will convert into saturated system. That is called heat of hydrogenation. Here the point is why we have to do heat of hydrogenation. Why we have to do hydrogenation? First of all, why we have to do hydrogenation? First of all, if we get to know what is hydrogenation, then we can move heat of hydrogenation. Okay. First of all, I am taking one system here. That is, for suppose CH2 double bond CH2 CH2 double bond CH2. This is alkene. Okay, I am doing hydrogenation to this system. In presence of nickel catalyst or any metal catalyst, platinum or anything, and I am heating here, right? What happens? Simple. You can go through radical mechanism also. So here radical cleavage, here also radical cleavage. I will get this structure, CH3 here, one hydrogen to this radical and one hydrogen to another. So here CH3 single bond CH3. So this is alkane, Now my question is, why we have to do hydrogenation? Here see, this is pi bond, this is pi bond, this is sigma bond. Okay, so which is strong? Pi bond is strong or sigma bond is strong? Sigma bond is strong, right? Why sigma bond is strong? Because of end to end overlap. Okay, so if you take internuclear axis as x-axis, for suppose, if px orbital of carbon and px of orbital of carbon, end to end overlap is there. For suppose the overlap is something like this. This is end to end overlap. So this overlap will give sigma bond, right? So if you have p by pz perpendicular to this px orbital, then we have like this. Okay, so this overlap will give you pi bond. Okay, so this end to end overlap will give sigma bond like this. So this is sideways overlap will give pi bond. So always sigma bond is stronger than pi bond. So that this is weak bond, this is strong bond, so that we are converting alkene to alkane. Because in nature or in universe, if you take one system, when we do one process or one reaction, definitely we have to move from unstable state to stable state. Here it is unstable, so we do hydrogenation, we will get the stable state. Okay. So in this process, what happens? First of all, we have to break this bond. In any reaction, breaking of bonds are there and making of bonds are there. So we are breaking this bond and we are making one new carbon hydrogen bond. So whenever one bond is breaking, in that process, what happens? We have to give energy. So this reaction is taking some energy. For suppose to do this reaction, to occur this reaction, we are giving 200 kilojoule per mole energy, right? 200 kilojoule per mole energy. All right. Okay. So in this, consuming energy is there, releasing energy is there, because bonds are forming. When one bond is forming, energy will release, heat will release. We have seen this type of reactions in thermodynamics, right? Okay. I'm giving 200 kilojoule per mole to proceed this reaction, okay, to break this bond, okay, everything to proceed this reaction. I'm giving 200 kilojoule per mole. This reaction, for suppose utilizing 140 kilojoule per mole energy. That means 140 kilojoule per mole energy is consuming in this reaction, okay. 200 minus 140, 60 kilojoule per mole. So 60 kilojoule per mole is releasing here, 60 kilojoule per mole is releasing here. So the released energy is nothing but your heat of hydrogenation, So the thing is, whenever you proceed for the reaction, whenever you do hydrogenation, alkenes will convert into alkane, that is unsaturated system is converted into saturated system to get stability, right? So in this process, what happens? Some energy is releasing. So this released energy is nothing but your heat of hydrogenation, okay. Now I'm asking you, in thermodynamics, whenever this type of reaction occurs, one energy release. If we give some energy, in some cases the energy will release. That is nothing but enthalpy of reaction. We have seen this term in thermodynamics. So this enthalpy of reaction, if heat will release, if energy will release, the enthalpy of reaction is nothing but exothermic. We have seen this. If you give energy, if reaction absorb energy, that is endothermic, okay. So for suppose, so this energy we can call it as exothermic, because this is the enthalpy of reaction, okay. We can call it as, in terms of thermodynamics, we can call it as enthalpy of reaction, okay. So this enthalpy of reaction now is exothermic or endothermic, because energy is releasing. So exothermic, whenever we have exothermic reaction, okay, whenever the energy is exothermic, what happens? We have to indicate minus sign. So minus 60 kilojoule per mole enthalpy of the reaction here. Enthalpy of the reaction minus 60 kilojoule per mole. Relate this with this. Heat of hydrogenation is 60 kilojoule per mole. Enthalpy minus 60 kilojoule per mole. So I can write heat of hydrogenation equal to here what I can write, minus of enthalpy of reaction. Why? Because enthalpy of reaction here minus 60, so minus of minus 60 kilojoule per mole, that means plus 60. So this is the heat of hydrogenation value. So I can write simply heat of hydrogenation equal to minus delta H, okay. So this is the conclusion. So the energy released during the process, during the hydrogenation, is called heat of hydrogenation. First of all, we are giving some energy. So in that energy, some energy is consuming in the reaction, remaining energy is releasing. That released energy is called heat of hydrogenation. So heat of hydrogenation equal to minus delta H. Okay. Now I'm giving one example here. So after seeing this example, you don't need to worry about the stability of alkenes. You can get to know. Okay. First of all, I'm giving here one example, that is CH2 CH3, CH2 CH3, here CH2 CH3, right? Double bond CH2. This is one example. Okay, this is one example. Second example. This is one example. Second example. here again carbon, here now CH2 CH3 CH2 CH3 and CH2 CH3 is here, here CH2 CH3, here hydrogen, here hydrogen, right, here hydrogen. So this is cis1. Okay, third one, now CH2 CH3, hydrogen, double bond, H, CH2 CH3. Okay, for suppose this is trans 1, this is cis 1. Okay, now observe which is more stable. First of all, I am asking you about the heat of hydrogenation. Which heat of hydrogenation is higher? So heat of hydrogenation is always inversely proportional to the stability. Heat of hydrogenation is always inversely proportional to the stability. Why? What is the reason? देखो, for suppose here there is an alkene, right? For suppose मान लो this is more stable alkene compared to these two, right? So whenever this stability is very very high, right, to break this bond I have to give more energy. Okay, reaction to proceed the reaction I have to give more energy. Okay, for suppose for this alkene I'm giving 200 kilojoule per mole energy. For this reaction also I'm giving 200 kilojoule per mole energy. Okay, to proceed the reaction, okay. So because of higher stability, what happens? Because of higher stability, what happens? It takes more energy to proceed, because bond is very very strong. To break this bond it need more energy. So to break this bond it absorb more energy. For suppose it is taking 160 kilojoule per mole energy it is taking. So the remaining energy 200 minus 160, 40. So it is releasing 40 kilojoule per mole energy. That means heat of hydrogenation for this molecule is 40 kilojoule per mole, right? Okay, so this is less stable compared to this. Okay, मान लो this is less stable, then compared to this it take less stable, so less energy, right? Because this bond is weak. To proceed the reaction it take less energy. For suppose it is taking 140 kilojoule per mole. So the remaining energy is 200 minus 140, that is 60 kilojoule per mole energy is releasing here. That means this is less stable, more energy is releasing, more stable, less energy is releasing. That means whenever stability of alkene is high, heat of hydrogenation of that particular alkene is low. Clear? Okay, now tell me which alkene is more stable, which alkene is less stable, which alkene is more stable and which alkene is less stable. First of all, first thing what you have to do, resonance, hyperconjugation, inductive effect. Okay, first I am comparing this one and this one. Okay, all right. So first of all you have to see resonance, hyperconjugation, inductive effect. So this is the order of stability. So whenever this is the order of stability, here resonance is not there. Okay, next see hyperconjugation. So for this double bond, this is alpha position, this is alpha position, right? So 2 plus 2, 4. So 4 alpha hydrogens are there. So 4 hyperconjugating structures. Next, for this alkene, this is alpha position, this is alpha position. So here also 4 hyperconjugating structures are there. Okay, 4 hyperconjugating structures are there. Here see, here alpha position, here alpha position. So here also 4 hyperconjugating structures are there. 4 hyperconjugating structures are there. So hyperconjugating structures are same. That means stability is same. Stability is same. Inductive, if you see inductive effect, according to inductive effect also ethyl groups only. So inductive effect is also same. So according to hyperconjugation, stability is same. Then what to see? Next what to see? Carbanion stability. carbocation stability. You have to see stability of reactive intermediates first of all. So with this we cannot do anything. Now we have to see stability of reactive intermediate. Stability of reactive intermediate. Okay. So for suppose I'm moving this bond here, right? And again I'm moving this bond here. What happens? What happens? Here carbanion, right? Here carbanion, here positive charge. So this hydrogen is participating like this, right? Okay. Here carbocation. So this hydrogen is participating here in this two. Acha. This carbon has minus charge now. This carbon has minus charge. Dekho. Here 1, 2 carbons. That means secondary carbanion. This carbanion is secondary carbanion. This carbanion is only one carbon. So primary carbanion. Acha. In carbanion, the stability order is, in last class we have seen, the stability order is primary carbanion is more stable than secondary. Secondary carbanion is more stable than tertiary. This is the order for carbanion. Carbocation, tertiary, secondary, primary, 0 degree, right? So this is for the carbocation. This is for the carbanion. This is for carbanion. Okay. So this is primary carbanion. This is the secondary carbanion. Primary carbanion is more stable. Okay. Primary carbanion is more stable. So this is the more stable one. So one stability of 1 is greater than 2. Stability of 1 is greater than 2. Okay. Next. 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 Acha. Next one. Now I'm comparing second and third. Now I'm comparing second and third. Dekho. I'm comparing second and third. Here see. For suppose if I move this bond here, same like this. I'm moving this bond. Again, hydrogen is participating like this. I'm moving this bond here. Hydrogen is participating. Okay. Acha. Now this carbanion 1, 2 secondary. This carbanion 1, 2 secondary. So this is secondary carbanion. This is also secondary carbanion. This is also secondary carbanion. Now according to the reactive intermediates also stability is same. Now what you have to do? Dekho. Here CH2CH3 bulkate group. Here CH2CH3 bulkate group. Here also CH2CH3 bulkate group are on same side. So repulsions are higher. Repulsions are higher. Right? So repulsions are high. Here CH2CH3, CH2CH3 are maintaining distance. So repulsions are less. So when repulsions are high, stability decrease. So that's why third stability is higher than second stability. Okay. So the conclusion is third stability is greater than second, 1 is greater than 2. Okay. Now I'm comparing third with 1. Third with 1. So again you have to see carbanion stability. Here the carbanion secondary carbanion. Here the carbanion primary carbanion. Right? So primary carbanion is more stable. Primary carbanion is more stable than secondary carbanion. That means 1 greater than 3. 1 greater than 3. So combinedly I can write as 1 is greater than 3. 1 greater than 3. 3 is greater than 2. 1 greater than 3. 3 greater than 2. So this is the order. Right? So 1 is more stable. Then trans is more stable. Then cis is more stable. This is the stability order. So 1, 3, 2 is the stability order. Okay. So 1, 3, 2 is the stability order. Right. So the stability order is 1, 3, 2. Heat of hydrogenation is inversely proportional to the stability. That means reverse. So heat of hydrogenation is 2 greater than 3 greater than 1. So this is the heat of hydrogenation. Okay, so to check stability of alkenes, what you have to do, first of all you have to see resonance, hyperconjugation, inductive effect. According to hyperconjugation, inductive effect, resonance, you have to check stability. If this one is not working, then you have to see stability of reactive intermediates, carbocation, carbanion. After that you have to see hindrance, that means repulsion is there or not. Okay, according to this you have to go, right? So next one next one, stability of conjugated systems. Stability of conjugated systems, first of all, aromatic is more stable. Aromatic is more stable than linear conjugated system. Linear conjugated system is double, single, double, single, double. This is more stable. After linear conjugation, cross conjugation is more stable. Cross conjugation is more stable. What is cross conjugation? See, this is cross conjugation. That means this double bond is in conjugation with this, and this double bond is in conjugation with this, but this double bond and this double bond are not in conjugation, right? So this type of systems are nothing but cross conjugated systems, right? So next stability is this. Next one, anti-aromatic compound. Anti-aromatic compound. So this is aromatic, this is linear conjugated system, this is cross conjugated system, this is anti-aromatic system. In linear conjugated, if conjugation increase, stability increase. For suppose I have this and I have this, right? Single bond, double bond, single bond, double bond. Here 3 double bonds, here 2 double bonds. So this stability is high, right? So this is about the stability. Okay, so I hope you people are clear about this video. If you have any doubts, please ask me in the comment section, right? Please ask me in the comment section. Thank you so much for watching.